as you start completing the steps, we'll eventually start discussing then what those steps are providing us. So I want you to right now look at AB, segment AB up there, and I want you to find the midpoint. Okay, find the midpoint of AB. Now, somebody in the last class, it's actually happened in every class today, said, well, I'm just going to look at the picture and find AB. Because you could probably do that. You could probably say like 1, 5, right? Okay? And you're probably right when you say 1, 5. But when you take, then, of course, exam, where you take the ACT, the authors of those tests know that you want to do that. So what are they going to do? They're going to give you points like that, where you can't necessarily just ballpark it and guess and get the right answer, right? Okay? You're going to want to use your formula. So every time that we do something in this class, you might be thinking, well, there's an easier way. I could just look at the line and determine that halfway between A and B in this case is 1, 5. Or maybe we're doing slope. You think, well, rise over run is really easy to look at and count and figure out that slope. On those other tests, you're going to need the formulas. So that's every time we do a question in class, we're going to use the formulas. Does that make sense? All right. I want to teach you in the way that you're going to have to perform and act on that test. Okay. So find the midpoint of AB. Remember, midpoints are found by taking your x-coordinates, adding together, divide by 2, and your y-coordinates, add together, divide by 2. Okay, so find that midpoint for AB. So everything we do here right now is for segment AB. Then find the slope of AB. If you remember, slope M is equal to y2 minus y1 over x2 minus x1. Okay, so once you find your slope algebraically with the formulas, okay, at that point, then it probably is a good thing to look at your graph and say, okay, if I would have counted rise over run, does it give me 1 over 1? And if I would have plotted the point 1, 5, does it look like it's in between A and B? It's the midpoint of A and B. So when I say we're going to use the formula, still don't say that's the only thing you're going to do. Still, add things back to your picture to verify that you've done things correctly. Okay. This problem is going to take us. Last class, it took us up to the bell. Okay. So it's pretty long. All right. Now, obviously, when you're doing it by hand on your own, you're not having somebody talk to you and tell you all the ins and outs of it. So it'll be a little bit quicker when you do it on your own. But it's very long. It's a long process, and a lot of the questions we see and problems we see in the next couple of weeks are going to be pretty long. But I would hate to make an error at 1.5 at finding that midpoint. Because if I make an error at 1.5, the next 40 minutes don't matter. Okay? Because the question's going to be wrong anyways. Does that make sense? If I make an error at that slope being 1, it doesn't matter everything I do after that because it's going to be wrong. So when you're doing multi-step tiered questions like this, periodically check to make sure you're doing everything right. Okay? Because we just did, in Algebra 1, finding the midpoint, or maybe Geometry Chapter 1, finding the midpoint. That is an individual problem by itself usually, right? Well, check that problem then. Okay? Check that you did it right. In Algebra 1, slope is an individual problem. You now have the ability to check that. Go back to your picture and see if that makes sense to you. Okay? So we've got the midpoint, we've got the slope. Now, the reason we want these things, the reason I want the midpoint and I want the slope of that thing is because I'm trying to find the perpendicular bisector of that red line. The perpendicular bisector of that side of the triangle. Okay? And we're going to write the equation of the perpendicular bisector. Okay? So we're going to go back to Algebra 1 stuff here for a while. But if I want to find a line that is perpendicular to AB, a line that is perpendicular to this red line. And I know the red line has a slope of 1, which is as a fraction 1 over 1, right? Okay. The slope of any line perpendicular to AB will have a slope of what? Right? You flip this, right? Which flipping it's kind of trivial, but we find the reciprocal, and then you change the sign, right? So that's positive 1, you change it to negative 1. Okay? So the slope of the line that we're interested in finding the equation for is going to be negative 1. Okay? Now I told you we're going to find the perpendicular bisector. So a perpendicular bisector is going to look something like that, so just a rough sketch right now. But is that slope negative? Does it go down, left to right? Yeah. Okay? So that should be modeled in my algebra here. It's going through, if it's a perpendicular bisector, it better go through the midpoint here, right? That's the part of the definition of perpendicular bisector. Okay? So now we want to come up with an equation. Okay? And we're kind of do a little bit of discussion here about what equations are for us. If I give you just an equation, don't write this down, but if I just give you a generic equation, y equals 2x plus 1. How many points are there on a line? Infinite. And if I ask you to write down all those ordered pairs, would you be able to do that? No, you would die doing it, right? Okay. But we still are interested in being able to do that. Even though we know it's feasibly impossible, okay, logistically impossible, we still want to have a technique that represents maybe all those infinite points. That rule right there, y equals 2x plus 1, is a way to get all those infinite points. Now we're not going to list them all at once, but if I want to know what is the point in which x is 0, what do I get when I plug x to be 0 in there? Y is 1, right? So I now know I've got a point 0, 1. If x is 1, what do I get for y back? 3. Okay. When x is 2, I get 5 back, right? So now I have a way, this is actually showing me this list that would be infinitely long, right? Okay. Well, for our problem right now, on this black line, do you know a point that has to be on that black line? C may or may not be. I'm not 100% sure. It might be, and sometimes it will be, but not always. But what point for sure is on that black line up there? D, right? D is 100% on there. So because I know that point is on there, let's use that fact to help us create our rule. I know that when I plug x to be 1 in, I should spit back 5 in my y value, right? Okay. Do I know the slope of that black line? Yeah, it's negative 1, right? Okay. Any line that's perpendicular to the red one has to be a slope of negative 1. So, here's some information that we have. We know 1, 5 should be on my line. We know m should equal negative 1. Okay? Using those two things to come up with the rule that provides all those infinite points, we're going to use this tool right here. Y minus y1 equals m times x minus x1. Now we use this, it was 4.2, 4.3, those sections. We use this in one of the examples in the homework. Okay? If you remember, it gave you like a coordinate plane and it gave you two triangles and I think they were red. They kind of looked like that. And there was this point right here that we had to find, point C. And in order to find that point, we had to come up with some equations of lines. Okay? We use this formula. We talked about this a couple weeks ago. We're going to use it again. Okay? You're going to use that formula several different times in this class beyond today. We're going to use it in Algebra 2. It's one of the main things you use in Algebra 2. First maybe couple months of Algebra 2. And when you get to maybe college algebra, if you go the integrated route, take some of those courses, guess what you use the first couple weeks of those courses? You use this. Okay? When I get to start teaching trigonometry after Christmas, we're going to start working with that thing to determine some features about triangles in trigonometry. So this thing becomes a friend to you. You get to calculus, You use that all the time. Okay, I'm taking graduate level math courses and I use that thing all the time. You're going to need y minus y1 equals m times x minus x1, no matter how far in math you go. Okay, you guys remember y equals mx plus b? Okay, well y equals mx plus b is exactly this thing right here. They are the same. Okay, most of you probably prefer y equals mx plus b. All right, but let me show you why they're the same. Don't write this down, but if I've got y equals mx plus b, okay, what does that b represent? The y-intercept. It represents where you cross the y-axis, right? So if I cross the y-axis, maybe let's put it right there. Okay? If that's fine, now I don't know what number that is. If I use the grids here, it's 2. But let's say I just don't know what that number is. Let's just call that number b. So that number, that y value is b, right? So what would the ordered pair be for that value? What's the x-coordinate for that point right there? 0. And the y-coordinate would be b, right? B could be 2, could be 3, could be a half, could be whatever it wants to be. Okay? Let's say that I know my slope for my line. Let's just say my slope is m. Okay? Let's start filling the information in that we know with this thing here. If I go y minus y1 equals m times x minus x1. Okay? This is referred to as point slope formula because you need a point that is on the line that you're trying to come up with the equation for, and you need the slope of it. Okay? Well, if I know my slope of the line I'm trying to come up with is just arbitrarily m, I would plug m in here. This y1 and this x1 are points that are on my line. It could be any point that's on my line. I know 0b is on my line, right? So x1 is 0, y1 is b. If I go y minus b, right? Y minus y1, m, x minus x1, but x1 is 0. I get that. Now this tells me y minus b equals mx, m times x, m times 0 is just 0, right? And then we always solve for y, and I get mx plus b. Does that make sense? So that is showing you that when you learn y equals mx plus b and you prefer that, it's because of this thing. They're the same. Okay? That's just kind of a special situation when you know that the point that you're using on this line is a y-intercept. Okay? And basically saying that this, we know that this value here is a 0. But this works all the time, whether x1 is 0, y1 is 0, x1, y1 can be any number they want to be. Okay? So this is a lot better than y equals mx plus b, defining equations. Okay? So let's do this. We know that we're trying to find the equation of that black line up there. We know that black line has the point 1, 5 on it. So there's my x1 and there's my y1. And we know that that black line should have a slope of -1. So I'm going to plug that stuff in to this thing. I'm not going to do any algebra until after I've plugged things in. So y minus y1, -1, x minus 1. Okay? I'm even, when I do this, because I know it's something that would really be a problem if I messed it up right here. If I have like minus a -1, I write out minus a -1 instead of changing it in my head to a plus. I'm very deliberate with this because I know how many more steps we're going to do, and it would be kind of a pain in the butt that if I made a mistake here and I do 20 more minutes of work, that 20 more minutes of work was pointless because I made a mistake here. Now what we do is this is point slope form. We don't like it in this way because of what we're going to do next, okay, or eventually what we're going to do with this. So we always like to put this into y equals mx plus b form. So we like to solve for y. All right, so we're going to try to get that thing all by itself. Well, this algebra kind of takes precedence, I think. You can add 5 to both sides, but you're eventually going to have to do this. What's this tell me I need to do? Distribute. So I'm going to have y minus 5 on the left. -1 times x gives me -x. -1 times -1 gives me +1, right? If I'm solving for y, that's basically when I say put it in y equals x plus b form. Another way of saying that is just say, take this equation and solve for y. So if I solve for y, what would I do next? Add 5. So y equals -x plus 6. So -x plus 6 should be the equation of that black line. Okay? Y equals negative x plus 6. Let me write this down so we're going to need it in a little bit. Equation of perpendicular bisector of AB is y equals negative x plus 6. Now what's nice is we should be able to kind of check that, clear this stuff out. If I want to check this, let's put, using maybe the algebra that you knew from last year, if I know that plus 6 is my y-intercept, I could put that there, right? And then the slope is a set of directions to get another point, right? So start the last point you plotted and then use that slope. Well, remember, slope here is negative 1 over 1. Rise over run. So it means down 1 to the right 1. If I go down 1 to the right 1, it would put me there. Down 1 to the right 1, put me there. Down 1 to the right 1, put me there. Okay? And if I start connecting those, my G's off a little bit. Let's get rid of that. Does that line look like the perpendicular bisector of the red line? Okay, now, I don't like to go off a look, so let's just verify some stuff. If I ask for, we know it's the midpoint. I'm not gonna ask for distances, but what is guaranteed here, if we've done this correctly, if that angle from E to D to B, too many in there, that angle should be a right angle. All right, so we have found the perpendicular bisector. Is that doable? Okay. Now, how does that relate to anything that we've done so far this week? It's exactly what we did on Wednesday. We did this on Wednesday, and we took a point. Let me actually clean this up and do it a little bit of a different way. We took any point, maybe point E, and we could move that anywhere we wanted to on this perpendicular bisector, right? And what was the conclusion that we came across on Wednesday that we were able to state about point E in relationship to point B and A? Yeah, it's equidistant. No matter where E shows up, it's the same distance from E to B as it is from E to A. Is that all right? Just keep that in your memory. And we're going to basically do the entire problem again, but instead of looking at AB, we're now going to maybe look at the blue segment, AC. Okay? So just to clean some stuff up, I'm going to, this gets really messy as I'm doing this. You can't do this on your paper. You want to leave, once you've drawn something in there, don't erase it. But I'm going to erase that perpendicular bisector, and now we're going to focus on the blue line segment AC, and I want you to find the midpoint of AC. I want you to find the slope of AC. Then I want you to find the slope of the line perpendicular to AC. And at that stage, we should be able to come back together and plug in all the information into this formula here. Okay? So do that. Find slope. I'll write this stuff up. I know it's a lot of stuff. Find slope. Midpoint of AC, slope of AC, and the slope of the line perpendicular to AC. Okay? And again, your formulas, these are things hopefully you've committed to memory. Midpoint, x1 plus x2 over 2, y1 plus y2 over 2, slope, y2 minus y1 over x2 minus x1. Okay, so use those things, come up with those quantities, and then we'll come back and create that equation. All right, just for the sake of time, if you haven't done that, hopefully we are able to do those things that quickly. But remember, midpoint is just adding your x's and divided by 2. So 4 plus 8 gives me 12. Divided by 2 gives me that 6. Add my y divided by 2, so 8 plus 0, obviously 8 divided by 2 gives me 4. Okay, so that's my midpoint. The next thing I want to do is find my slope of AC. So slope of AC, y2 minus y1, so 8 minus 0 gives me 8. 4 minus 8 gives me negative 4, so my slope is negative 2, right? That's the slope of the blue line up there on the smartboard. We want the slope of any line that's going to be perpendicular to that. Okay, so we take the reciprocal of 2, which is 1/2, right? Okay, and because 2 is negative, we want to make sure that our slope that we end up using is the opposite sign reciprocal. So instead of, when it's negative 2, the opposite sign reciprocal is going to be positive 1/2. Okay, and just to kind of convince you guys of this, how many lines are there perpendicular to AC? There's a lot of them, isn't there? All of those lines are going to be perpendicular to AC, correct? Well, if I ask it to define one of those for me, and I change this into y equals mx plus b, look at your slope right here, it's 1/2, right? Any line that is perpendicular to AC, does that slope ever change from 1/2? No. But how many of those lines that are perpendicular to AC pass through E? Just the one, right? So that one that we're looking for right here, we know a point that it passes through. We know it passes through 6, 4, right? So we're going to use our algebra formula of y minus y1 equals m times x minus x1 to convince ourselves that we do end up getting 1/2 x plus 1 for that equation. So if I've got y minus y1 equals m times x minus x1, remember your midpoint in this case is x1 and y1. Okay, we're using the midpoint, but in general, because this might be a concept that we use other places other than just perpendicular bisectors. If they ask me to find a line that's perpendicular that passes through A, okay, well then instead of using 6, 4, I would use 4, 8, right? Because that's the point A. If they wanted me to find a line that is perpendicular to AC but goes through C, I would use, instead of 6, 4, I would use 8, 0. Does that make sense, everybody? They're going to tell you somehow what x1, y1 to use. And by saying find the perpendicular bisector, they're telling you to find the midpoint and use that as your x1, y1. So we go y minus 4, slope was 1/2, and then x minus 6. Okay? Y minus 4 is equal to 1/2 x minus 3. I just need to distribute that, right? Okay, so 1/2 times x is 1/2 x, 1/2 times negative 6 is negative 3. Now I want to solve for y. So y equals 1/2 x plus 1, right? And that is what GeoGebra was showing us. Okay? I like, we talked about how powerful GeoGebra is, but it does a lot of the algebra for you. That's why I want to use it in conjunction to showing you the algebra, doing the algebra, practicing the algebra. If this was like a, my college algebra class, my trig class, I teach calculus, I use GeoGebra to do all that algebra 1 stuff for us, right? Because if you're in calc, you should be pretty proficient at algebra 1, right? And I understand that we're not in calc. We maybe forget a little bit of algebra 1, so we're going to practice this stuff by hand. But eventually you get to a stage where you could use technology to do some of that preliminary stuff for you. I want you to use this technology to double check the things you've done by hand. Okay? So now we've got that equation. That's the equation of perpendicular bisector of AC. And it is y equals 1/2 x plus 1. All right. Now I'm going to go back and put a point on that perpendicular bisector. Okay? I put a point on that perpendicular bisector. right there. I'm going to call it point P2. What could you guys tell me if I looked at P2 and I started moving that? Wherever I put it, it's going to be equidistant from what two things? A and C. Okay? Would you guys agree that at some point, when I have both these perpendicular bisectors in there, that at some point P1 might land on top of P2? You guys agree with that? Okay? Well, that point turns out to be very important to us. Okay? So we want to find that. Okay? And what I want you guys to realize is that finding that is a Algebra 1 concept that you guys have done in the past. If you were in Algebra 1 and they gave you, it was in the concept of systems of equations, if you're interested in finding where two lines intersect, where y equals negative x plus 6 intersects with 1/2 x plus 1, if you're interested in seeing where those two things intersect, you know that when they intersect, would you agree that when those two lines intersect, their y values are the same? Okay? So if I come over here, let's look at, okay, that point right there, on that line, that y value is probably about 3, right? Around 3, okay? If I look at that line, is that y value around 3? So when those two lines intersect, do they both share the same y value? So if these two things intersect, which they obviously they do, these y values are going to be the same when they intersect. So if those y values are the same where they intersect, what's that tell you about the x values, or the components that help us find y values? They're equal. They're the same. Okay? Back to substitution in regards to the systems of equations. These two things are equal, so those two things are equal. So I want to say negative x plus 6 is equal to 1/2 x plus 1. Okay? Now that's an equation that has some fractions in it, right? Not a lot. The fractions that we developed here are a lot easier than the ones we've done in 6th and 5th period. 6th and 5th period had, and we ended up getting fractions that were, 5th period especially, it was like 135 over 19 and stuff like that. It was really ugly. But here, what can I multiply everything by to get rid of the 1/2 fraction?
2.
Yeah, multiply everything by 2. And it's got to be everything. So I'm going to multiply negative x by 2, multiply the 6 by 2, multiply the 1/2 by 2, so it gives me 1x, and multiply my 1 by 2, it gives me 2. Okay? You just multiply by that common denominator, right? We'd like it to be the least common denominator. In this case, it would be 2. But it doesn't have to be. You can multiply by 20, it would work. You can multiply by 22, it'll work. Multiply by 422, it'll work. We just want to get rid of fractions. Okay? So now, solve that for x. Add 2x to both sides, so you get 3x. I'm going to remove 2 from both sides, so I get 10. So x becomes 1/3, right? No, sorry, not 1/3, 10/3. And 10/3 is 3 and 1/3, right? Or 3.33333333. Somebody in the last class said, let's put it as 3 and 1/3. Let's write it as a mixed number. Nothing wrong with that, but we're going to do something else with this number. We won't plug that number back in to find y, because we're interested in the y value where these lines intersect. And 3 1/3 as a mixed number, mixed numbers are terrible for us. Think about this. If I want to do any work, if I let x be 3 1/3, and I take that 3 1/3 and plug it back into one of these things to find y, I got to take 3 1/3 and transfer it back into 10/3. Does that make sense? So never use a mixed number. Mixed numbers were good in 3rd grade for telling me that I have 3 whole pies and 1/3 of a pie. But it does nothing other than that for us. Does that make sense? Never use them. They're terrible. Okay? Even for decimals are bad here, because 3.3 or 3.33 or 3.3333, they're all maybe good and better approximations of 3 1/3, but they're all still, no matter how many 3's I put on there, they're still actually terrible approximations of 3 1/3, right? Or 10/3. So leave it as 10/3. We're going to deal with that one. Okay? If I round it, it's not going to give me the exact y value that I'm interested in. Okay? So when you solve a system, you find x. Just like any other system, you plug it back in to find y, right? So it doesn't matter which equation you want to plug into. Plug into the top one, we get y equals negative x, so now negative 10 thirds, and then plus 6, right? Is that doable? If I plug it into that one, I want to add those two things together. How do I add two fractions together? You need a common denominator. Right now that denominator is 1, right? It needs to become 3. So what's the top need to become? 18. Okay? I always double check, make sure if I divide that, do I still get the 6? And I do. So now we can say y is then equal to 8 thirds, right? Leave it as 8 thirds. I'll write that as 2 2 thirds. Okay? Same thing would have happened now, because it doesn't matter. Do it right here. If I go y equals, plug in this bottom one, 1/2 times 10 thirds plus 1. Now I got to multiply those fractions. So it's 10 over 6 plus 1. Okay? Well, if I'm going to add those together, I need a common denominator, so that becomes 6 over 6, right? Well, that gives me 16 over 6. Okay? How many times does 2 go into 16? 8. How many times does 2 go into 6? 3. So it doesn't matter. It just might, I think it looked like it was easier algebra there to plug into the blue one instead of the purple one. So that point right there, that point where P1 and P2 kind of collide, where they intersect, we say that those 2 points are concurrent there. They occur at the same spot. Okay? Go ahead and put all this stuff back in there. Get those out of the way. If I were to ask it to plot 10 thirds, comma, 8 thirds. It's that point right there. Okay? Now, let's talk about that point. Okay? Because that's what this question is about. We started with those 3 points, A, B, and C, and we want to go through all the algebra that defines H for us. Okay? And now we know that that point is 10 thirds, comma, 8 thirds. But what is that point? Here's the geometry. Okay? That point, you guys told me that any point on this line here, so any point like P1, is equidistant from A and B no matter where it's at, right? So if I put P1 right there, is it equidistant from A and B? Yeah. Okay? So I'm going to write that down. We're going to write, I'm going to get rid of this stuff for now. Okay, so wherever P1 is, if P1 is right there, you can tell me that P1 to A and P1 to B were the same, right? But instead of calling it P1, let's call it H. So you can tell me that H to A was equal to H to B. Not doable? Any to H? Because it's on the perpendicular bisector of AB, right? It's got to be the same distance from A as it is from B. All right? Now if I look at P2, P2, no matter where it's at, is going to be equidistant from A and C, right? Well, what if P2 is right there? What if P2 was H? Would H be the same distance from A as it is from C? So could I say H to A is equal to H to C? Does that make sense, everybody? I have the idea, and I'm going to write it this way. I'm going to say HB, just so you guys see it a little bit better. HB and HA, I'm going to write in that order. HB is the same thing as HA, and HA is the same thing as HC. Can you do this? And say that HB is the same thing as HA is the same thing as HC? So what that point H is for us is it is the one point out of the infinite number of points that exist. Okay? Get rid of P2 there. H is the one point that if I stand on H, I could walk to A, walk to B, or walk to C, and the distance be the same. Okay? No other point in the whole coordinate plane does that for that triangle. All right? Now, if that's something that can happen, let's think about this. Let's say that I have just H to A, Okay, now I don't think I can really do this the right way because it's going to just the way my mouse works. If I walk H to A, and now I start to swivel that and get H to B, and then swivel that and get H to C, and then swivel that back to get H to A, what shape would I have just traced out? Circle. So this H is a particular important point in regards to centers of triangles, okay? And it's the center of a circle. Then when I click on H and then go click on A, okay, when I draw a circle centered at H and it passes through A, what does it do to B and C? Passes through B and C, okay? Every single triangle, and you've heard me say this before in the past, every shape that we deal with is usually related somehow to a triangle, right? Circle related to a triangle, okay? That point, H, the intersection of perpendicular bisectors, is referred to as, one word, circumcenter, okay? But you guys have seen that word circum before. Where in math have you seen the word circum, the prefix circum? Circumference. Circumference referred to the what? The circle. Around the perimeter of a circle, right? Okay. So when we see the word circum or the prefix circum, it's referring to some type of circle. If I say the word circumvent, if I say don't circumvent the work, okay, that means don't go around the work, right? Okay, I want you to do the algebra. I say that all the time. Don't circumvent something. So whenever you say circum, it means to go around. Okay? The center is the center then of that circum, sometimes called a circumcircle. Okay? But other times, this circle is referred to, this is the way we're going to talk about it. The circle is called the circumscribed circle. Okay? You guys talk about Miss Jones' class circumscribed, don't you? Yes, you do, you liars. This is a vocabulary word a couple weeks ago.
Yeah.
Okay, I'm not even in class and I know that. Okay, so circumscribe means to draw around, right? Okay, well, circum means circle. Okay, scribe, think about like what you learned in world history about people that recorded history. What were they called? Scribes. They wrote things down, right? They drew things out. So circumscribed is the circle that is drawn around a triangle. The geometry concept of it is that we have to hit the three vertices of the triangle. And every single triangle has one of those circles, no matter how big the triangle is. Okay? Now, those points, though, that circumcenter, and I think I've constructed this so it's dynamic, where I'm going to move some stuff around here. Let's kind of see, what type of triangle would this be? It might be. It does look like it, but let's see here. I'm going to put angles in it, and we'll identify them in regards to the angles. So, all right, so we get those angles. So we got 56, 71, and 52, right? So based off those numbers, what can we classify it as? It's scalene, okay. But on the angles, it's, if they're all smaller than 90, they got to be all acute. Okay, so that's an acute triangle, right? Scalene's 100%. You guys are 100% right. There's nothing wrong with that. In an acute triangle, the circumcenter is on the inside of the circle. Okay, let me move some stuff around here. That point H, I don't have it because of how I wrote the, hold on a second, we'll get it. Perpendicular bisector to that, perpendicular bisector to that, okay.
Please pardon the interruption. This announcement's for the principal of Foods kids that made the chops and potatoes today that sound really good. Be sure to pick those up before you leave the building today for the weekend. Principal of Foods students, please pick up your leftover food before you leave. Thank you.
Okay, so H is the circumcenter, right? As I move this triangle, notice how H starts to move as well, right? Well, when I move that triangle to create that type of triangle right there, what type of triangle is that? A right triangle. Where is that circumcenter? On the hypotenuse. And even better, it's where at on the hypotenuse? The midpoint, okay? A lot of the homework questions you guys will see next week actually allow you to do that, okay? And allow us to find that circumcenter, the ordered pair, so much easier by using that relation. But as I make that angle beyond 90, where does the circumcenter go? Yeah, it goes on the outside, right? Yeah. So as you're doing this stuff, your circumcenter does not matter where it's at. Could be on the inside, could be on the outside. But its location tells you maybe something about your triangle. Or the type of triangle that you have tells you something about where the location of the circumcenter should show up. Okay? We're going to keep working on this. That's one center of triangles that's very important. We're going to learn 3 more. No. Yep. Some of them are a little bit easier than this. Some of them are a little bit harder to where we don't necessarily have the algebra in order to do them. So we'll just kind of talk about them, but we won't get to them as deep as what we just did here. Okay? But it is always on the end of course exam. Can you write, whether it's in this respect to this type of problem or not, they're going to ask you to come up with equations. Okay? Can you develop equations? So we're going to work on that a little bit as we learn the geometry. Okay? No homework tonight.